JFET regarding the depletion layer and the pinch of voltage VP. How we have taken it for two cases and we have analyzed in our previous session. Continuation of that, we're going for session 3 of continuation of JFET itself, and we'll see for the N channel and P channel JFET. That is how the JFET gate to source voltage variation exists. Previously we had seen with respect to the drain. Now we will see the JFET gate to source voltage variation, how it is exist, and the operation of JFET at various gate bias points, and finally the characteristics, that is the drain characteristics of an FET. For the JFET gate to source voltage variation to be considered here, for a constant gate voltage, varying drain to source voltage, then it yields a single drain current, and the voltage between the drain to source characteristics curve can be drawn in variation with the gate voltage with a constant and a small drain voltage. And this can be looked further into the effect of the voltage between the gate to source variation. Now, here in this diagram, we can see that there is a variation between here the voltages and the current. This is called as a VI characteristics. Okay. Or the relation between your VDS and the ID. Recalling from the previous discussion that if VDD is small, then VDS is also small, and the channel width, the width of the channel is essentially constant. So in the figure, we can see that the increasing width, in the figure we can see that the increasing width of the channel will give rise to the increase in your ID. Okay. Now, as the increasing width of the PN junction, that is in the previous case we have seen that the depletion layer, that it gets closed, then we tell it is a pinch off. Pinch off occurs only, pinch off voltage will occur only for lower values of your VDS. If VDS is varied, here we can see if VDS is varied, then the pinch off voltage, namely V suffix P, will occur only for lower values of your drain to source voltage. By combining the effect of your VGS and VDS, by combining the effect of the VGS and VDS, we can see there is a family of characteristics curves similar to the similar to your BJT, whatever we have done in the previous module. Okay. As VGS is more negative, observe here, as VGS is more negative means for N channel we are talking about. Here for the N channel we are talking, as VGS is more negative, a value of the VGS is reached for which the channel is completely depleted. Completely depleted means no free carriers and there will be no drain current. When there is no drain current, the channel is completely closed. Then ID is equal to 0. When ID is equal to 0, a pinch of voltage occurs. Okay. And the threshold voltage for the N-channel JFET is negative. That is, the pinch of voltage V suffix P is less than 0. We can say it is less than 0. The pinch of voltage. So this gives the relationship between your VDS and ID curve. Now, if we apply the VDS variation, like as and when the VDS is being increased, this VDS variation effect, we can see that the pinch of voltage will occur only for lower values of VDS. Since we have very less of a channel to start with, resulting in the lower values of your drain current at the pinch off. By combining the characteristics or the effect of drain to source VDS and VGS, voltage between gate to source variation, a family of the characteristics curve, a family of these characteristics curves represents that can be increased for the N channel. We can see that here when VGS1 is equal to 0, you can see IDSS occurs, that is drain to source current occurs. Next, when VGS2 is less than VGS1, when VGS3 is less than VGS2, when VGS4 is less than VGS3, when VGS is less than or equal to VP, then we can see that the current keeps on decreasing. Whenever there is a drain current keeps on decreasing, when we come VGS4 is less than VGS3, we can see that the drain current is reaching almost to your 0 point or the null point. The polarity of the VDS is switched since the majority carriers are holes. The current flows out of the drain terminal, yielding to the negative current with respect to the conventional current direction, that is drain to source directions. The threshold voltage of this will be at a lower values. Okay, next coming to your P channel. P channel, as I told you, if we understand one channel, then the other channel will be easy. Now, if you see here, everything is the same, but the positive value of VDS, here's a negative value of VDS, and VGS is less than, always. Here it is always a less than symbol, here it is a greater than symbol. Okay, and this is also is a minus ID. So for a P channel JFET is analogous to the N channel FET. The polarity of the VDS is switched here since the majority carriers are holes. Okay, the polarities means here it is negative, here it is positive, right? The polarity of the VDS, that is voltage between the drain to source, is switched since the majority carriers are holes. The current flows out of the drain terminal, yielding a negative current with respect to the conventional current. That is, which is the conventional current here? The current flowing between the drain to source was defined as a positive direction. Right now it is becoming negative. Hence, here for an N channel, pinch off occurs when VGS is greater than or equal to VP. But for a P channel, the threshold voltage of the P channel JFET is more positive, and the channel is depleted only when VGS is greater than or equal to VP. This gives the comparison between the N channel and the P channel. The operation of a JFET at various gate points whenever there is a bias between the gate. In the first case, we can see that the bias is 0, means there is no gate voltage which is being applied. Then what happens? The depletion layer is very, very thin. Here the depletion means this zebra shaded part. The depletion layer is thin. So the low resistance channel exists. This is a N channel exists between the drain and the source. This is the first case. Next, if I start applying the voltage, that is gate to source voltage, then VGS, if it is lying between 0 to your VD, then what happens? The moderate gate to channel reverse bias result in narrowing the channel, N channel. Okay. Now, still more, it has been biased. That is, here the bias of the gate is more. The bias is greater than the pitch of voltage. Then there is no conducting path and the ID current doesn't flow. The channel is completely closed. When the channel is completely closed, then no current flows. The point at which the channel just gets closed is the voltage at which the voltage where we are applying is called as a pinch of voltage or the pinch off point. These diagrams, all these three diagrams, represents the operation of a JFET at various gate bias potentials. Next, coming to the drain characteristics of JFET. In the drain characteristics of the JFET, we have to consider, let us try like considering what happens when there is a variation of the gate voltage from 0 onwards. Now, let us try to summarize the function of a FET through which we can obtain the characteristic curve also. Characteristics curve of a JFET, which is called as a drain characteristics. The circuit in this FET is to obtain the drain characteristics. This circuit in this FET is when the voltage between the gate to source, that is when VGS is 0 or they are shortened, when VGS is very, very less, the ID, the current, that is drain current from source to drain is also nil. And there is no VDS applied. As the voltage between the drain and the source, VDS keeps on increasing, that is drain to source voltage keeps on increasing, then the current ID starts flowing from source to drain. This increase in current is linear up to a certain point called as knee voltage. This up to a certain point called knee voltage. I repeat, when the voltage between the gate to source, that is VGS is 0, or whenever VGS is very negligible, the current ID from source to drain is also nil and no VDS is applied. This is first case. Now, we will see that the voltage between the drain to source, that is VDS, is increased a little bit. Whenever the VDS is increased, see, whenever the VDS is increased here, whenever the VDS is increasing, the current ID starts flowing. Whenever the voltage increases, the current also increases. VDS is increased, the drain current also increased from the source to drain. This increase in its current is linear up to a point A from this diagram, up to a point A, and this point A is called as a knee voltage. The region from the origin O or the 0 to this point A is called as a ohmic region because it behaves as a resistor here. The gate terminals will be under reversed bias condition, and as ID increases leading to the pinch off. Okay, as ID increases, the depletion region tends to constrict. This constriction is unequal in length, making these regions come closer at drain, and further the channel gets closed. This we already have seen and we have termed as a pinch up. This leads to the pinch of voltage. The pinch of voltage is defined as the minimum drain to source voltage where the drain current approaches a constant value, that is the saturation value. Okay, so this is called as a pinch off from A to B. The point at which this pinch of voltage occurs is a pinch off point denoted as B. This is called as a pinch off point denoted as B. As VDS is further increased, as this VDS voltage is further increased, the channel resistance also increases in such a way that ID, the current ID practically remains constant. Thus, this point is up to point C. The region between the point B to point C is known as a saturation region, or it is also called as amplifier region. All these along the points A, B, C are plotted here. Beyond C, what happens when there is beyond C? When it is the drain currents here, it just shoots up. Okay, and it just enters into the breakdown. The drain characteristics is plotted here between the VDS and your ID. The overall picture of variation of ID is given here, including the ohmic region, saturation region, and the breakdown region. As the negative gate voltage controls the drain current, FET is called as a voltage control device. The drain characteristics indicates the performance of an FET. The drain characteristics here, the obtained values are the drain resistance also it is called. Okay, transconductance and the amplification factor. Okay, so this graph represents the drain characteristics, which gives the relation between VDS and ID pictorial graph, which clearly illustrates the type of your ohmic region, saturation, and the breakdown region. Thank you.